Another week, we're getting there, and then we're going to jump back into hydrothermal deposits, and specifically today looking at late stage magmatic systems, something that you guys know more about than I do now after your tenement project. So maybe you should be giving this lecture, but I look forward to checking out those videos going forward and seeing how people did with their bottom line. Hopefully there's been some money made, or maybe lots of money lost. All part of the fun of being involved in economic geology. So today, we're going to go through some more deposit models in the next couple of weeks, mainly around hydrothermal systems. These are some of the most commonly developed ore deposit systems in terms of specific metal commodities, but they're also quite difficult to find. And so just remember that we have generic ore deposit types. I've always liked to think as economic geologists as terrible pigeonholers or stamp collectors. And they're based on detailed analysis of specific ore deposits in, type examples. And in reality, that's not very true or fair. We have mixing of different types, and some type deposits have very specific circumstances. So it's very important, I find, to think about them in terms of a process. Okay, so they're broader processes, and yes, we have type examples, but don't get too bogged down in some of the specifics of those, and more think about the generic features of them, because that's what's going to help you find one or when you work on one. So think about things like the host rock types, how alteration would affect them, the styles of alteration, that is their conditions and variables involved in them, style of mineralization, the common tectonic settings, the composition of the hydrothermal fluids, and age of the deposits can be important, as we discussed earlier in the trimester. So this is the way to think about it in terms of a process, and less so about, we see this specific rock type, and if we don't see this specific rock type, there can't be this style of deposit. I don't agree with that sort of thinking. Work more towards it's very similar based on these features. So yeah, this is just summarizing this sort of point. Models should be regarded as end members, and we have common features, and it'll be a spectrum of aspects that can be occurring, and just to be wary of this sort of environment and the processes involved in forming that ore deposit, and less so sort of tick box exercise of relationships to a type deposit, which its nature, there's probably very unlikely that you can get exactly the same features in a type deposit, say in South America versus in Africa. Geology is quite diverse. Okay, late stage magmatic deposits, surprise, surprise, where they mostly occur is subduction zones. The most dynamic tectonic setting on the planet, and where we have most continental magmatism. Okay, most magmatism occurs at mid-ocean ridges, but the stuff that produces continents, occurs on continents, happens at subduction zones. It's a prime spot where we actually refine and build continental crust, and we can also destroy it by taking material down into the mantle. So it's a great spot for nature concentrating particular elements. So remember, the continents are rich in silica, aluminium, things like this. They're felsic. So we have this refining of the material, predominantly elements that like to be in the melt and differentiate in a magmatic system. So they're obviously going to be a nice breeding ground for specific commodities, especially in magmatic processes and hydrothermal processes associated to magmatism. So things like porphyry copper, porphyry gold, porphyry moly. We will also get epithermal gold and silver. And so quite a diverse setting. We might get magmatic deposits, you might get pegmatites, etc. So the main reason we get lots of magmatism in these settings is we have the fluid released off the subducting plate, intersecting hot portions of the mantle that promote melting, and the movement of magma into the crust leads to its differentiation and additional melting in a high heat flow environment of the magmatic arc. So we can get additional and more felsic melts, and we can progressively move material and concentrate elements and commodities in particular from the mantle or the lower continental crust to the surface, where we can get processes that enable us to concentrate them sufficiently for an ore body. So we can also get aspects of rifting in the back arc, things like the Taupo volcanic zone, or examples where we actually have pulling of the material away from the trench, and that can help produce additional epithermal deposits. In particular, we might also get some orogenic gold. We might get base metal VMS style deposits there, but we'll talk about a bit more about those types in the next lecture. Okay, here's just a fancy 3D diagram to show you some of the diverse dynamics of convergent or subduction zone margins. So in the first case, we have our standard system, slab subduction, dehydration. We have the corner flow in the mantle wedge leading to melting. When this melt rises, we might get additional melting in the lower crust from this high heat flow. And this moves up to the upper crustal system where we produce volcanoes, spurting out all manners of material, including their hydrothermal systems up here, and in the sort of roots of these volcanoes or in the magma chamber, we can get things like porphyry, copper, moly, gold systems. So that's the fairly standard model. You can think of places like South America is classic for this, and Eastern Australia represents a paleo subduction system where we no longer have subduction going on, but we had subduction active for over 500 million years in Eastern Australia. On alternative circumstances, we might collide or accrete a terrain. So this could be an island arc, or it could be a seamount or something like this, and this clogs up the accretionary or fore-arc region of the system, and this might change the nature of the slab. It might break off, or we might get a reduction in the fluid flow and melting dynamics here, and we could actually, drive metamorphism that can help produce things like orogenic gold deposits, but they also might produce limited melting and collision-related porphyry copper systems, as well as maybe dynamics in the back arc. And, we can go into different complexities of this process and how they might control different porphyry systems, but for this level, we're going to mainly worry about the standard run-of-the-mill style. Sorry, my apologies. So granite-related systems. As the title suggests, they're dominantly granitic. So most of the time, these magmas that are rich in metals are felsic, because that process of going towards a felsic magma concentrates the metals. They're incompatible. They don't generally like being in minerals, so they stick in the silicate liquid, and that concentrates to the felsic end member. In turn, these magmas are generally wetter because water does the same dynamic. It likes to stick in the melt, and so it concentrates into these felsic systems. And the processes occur at various depths, but generally they are most common at the upper crust. So granite in this sense includes the broad magma types, but what happens is if we concentrate this fluid, particularly in the upper crust, we can exsolve it by processes like first boiling, so a depressurization, and that can actually then release the metals into the fluid that can move into the country rock and deposit out, or even in the granite, and this contributes to its hydrothermal alteration in both the granitoid and the country rock, as well as mineralization. So here's a section through a high-level granite undergoing progressive crystallization. So the grey areas represent zones of fluid saturation in the residual magma. So fluid has reached a point where it can no longer just stay as a component in the liquid, it crystallizes out as a fluid, in this case a water-rich fluid. This could be related to depressurization or first boiling, or the progressive crystallization and concentration of that fluid as a secondary boiling process. And this fluid takes incompatible elements, and particularly the metals, and then can lead to deposition of them into the system. So what then happens is we get a circumstance of hydrofracturing, so the pressure of the fluid exceeds lithostatic conditions, and that's easier to occur at shallow crustal levels. So we could generate breccia pipes where you have significant overpressure and we fracture the rock around the conduit, the fluid conduit, or we could get localized veins, so more concentrated sheeted vein systems or simple vein systems carrying that fluid from the top of the granite closer to the surface. Remember, the fluid is buoyant and wants to move upwards. So this is another schematic highlighting this. We have standard crystallization of the granite. We might start with about 3% water. As we crystallize things like feldspar, quartz, biotite, and hornblende, we are concentrating that water. We have relatively limited hydrous minerals, and it petitions with it metals like copper, lead, zinc, silver, gold, moly, tin into that fluid phase. They like to complex with chlorine complexes, so they're also saturated in this area, as well as fluorine, sulfur, boron, etc. So this becomes a classic spot for metal concentration, and then in essence, if we can release this material, we can produce mineral deposits in this main area. So we might have sheeted veins, breccia pipes going on out of this section, and this area, top portion of this pluton, might form a Grison style or a porphyry style deposit, depending on the nature of the host granite. So you can see that the actual composition of the magma is directly related to its metallogenic potential. So if it's fertile or barren. So we know the broad types of granites, I and S. So I is predominantly from igneous types, or is metaluminous. S type is from sedimentary rock types, so it's really potassic or peraluminous. They can actually produce different mineral deposits, and we'll go through that in a second. And this is one of the primary controls leading to variations in deposit type, from porphyry to intrusion-related gold, grisen, etc. But this is the style of the system, and we have this boiling of water out of the granite that can deposit the metals. So I-types mainly derive from mantle input. They are relatively dry, low in water content compared to S-types, 2 to 3 weight percent versus 7 to 8. They're generated deep in the crust, and they can rise fairly shallow to fairly shallow crustal levels. You know, these are the classic Andean style magmas, and they form adjacent to subduction zones. They're relatively hotter because, one, they form at higher temperatures. They're also drier, which contributes to forming hotter magmas. So they predominantly can exalt fluid phase by first boiling, associated to decompression, before significant fractional crystallization. So that's a key that might influence the metal deportment, because metals are mostly incompatible, but some can get caught up in early crystal products. So this promotes early metal extraction, accompanied by brecciation, hydrofracturing, and circulation of hydrothermal fluids, this boiling process at shallow levels. So it's very good for things like porphyry deposits. I-type granites are classic for porphyry deposits. And this is where additional factors become very important. Oxidized magmas are common for, I-type magmas are commonly oxidized. They're generated in a mantle zone that is oxidized, and their unique water contents actually influence crystallization history that promotes copper concentration in the late stage of the differentiation, or in the shallow levels, over things like moly. So moly is highly incompatible, but the lower water contents restrict fluid saturation to very late stages, and copper will deport into things like biotite, but it hasn't done so related to the fractional crystallization. So it actually gets to a point where it can get to a significant concentration during that boiling and release as porphyry system lots of sulfides, despite this system being unfavorable in a purely oxidized sense for sulfides. But the dynamics of the crystallization and the relatively oxidized condition contribute to petitioning of copper and the crystallization and mineralization in porphyries. So if they erupt I-types, they produce rhyolite. They're generally hotter and can rise faster and further than S-type magmas. So here's just an example. Here we have our classic S-types, peraluminous, relatively potassic, red aluminium, commonly contain biotite muscovite, as well as maybe cordierite, andesite, and garnet. Our I-types, metaluminous, dominated by pyroxene hornblende biotite, relatively potassium poor, and peralkaline is a distinct type, very sodic, characterized by unusual minerals like edgerine, riebeckite, densenite. So these are the two to mainly worry about. So if we go back to our porphyry deposits, as I was discussing, these mostly occur in magmatic arcs because we have these unusual circumstances where the magma can get to very high crustal levels. It's oxidized and generates that fluid overpressure to form a porphyry style. There's several different types. The main types is a copper gold versus a moly copper. So one dominated by copper, the other one dominated by moly, but you can also get tungsten porphyries as well. So the copper gold ones are oxidized pollutons, predominantly I-type. You can also get reduced S-type tin tungsten systems. And this also relates to their crustal depths. So shallow copper gold systems versus deep tin and tungsten. So the relative change in these processes associated with how the minerals crystallized and the nature of the crystallization sequence. Here we can concentrate copper to late stages, whereas in these reduced systems, copper and the sulfides can form very early on, whereas tin and tungsten form predominantly as oxides, and they are left to the late stages and concentrate in those systems. So it's relatively distinct processes. So here's a schematic of a porphyry deposit. So as we stated, the hydrothermal fluids related to late stage magmatic exsolution, we get strongly developed hydrothermal alteration. We have the top zone is dominated by potassic. The relatively hot zone is potassic. At lower temperatures, we get a sericite chloride style. And then at the top, we have our sort of fumarole, and this is where our hydrothermal system or volcano is existing. So the fluids concentrate metals in this potassic zone, in the upper levels here, in the porphyry system, and we might get some higher level processes like epithermal or maybe even skarn processes adjacent to it. So this is our epithermal system where we have groundwater and very late stage hydrothermal fluids coming off. But we'll talk more about epithermal in the next lecture. So we have a very zoned alteration style, which is quite potassic, changing from sericitic to potassic. So the deposits are characterized by multiple overprinting veins because we have substantial overpressure. They have low sulfide content. We have this balancing game of the oxidized potential contributing to copper or moly partitioning. They are generally large tonnage, but low grade. So Cadia is a classic example, fairly low grade, but a very big deposit for gold. And here's just a more complete diagram from Sillitoe. And here we have a generalized alteration style. We have our potassic porphyry system here, top level. Further down, we might get sodic calcic. We move into a chloride sericite or sericitic. And then in the upper levels, we have, quartz porphyroid, quartz lunite systems, maybe kaolinite. And we also are surrounded by prophylitic alteration. But we must take care because this is largely a metamorphic effect with limited metasomatism. So this is where most porphyry deposit is. So like I said, South America has the world-class ones. Chuquicamata, Escondida. These are some of the world's biggest porphyry copper gold deposits. But Australia also has a few related to ancient subduction zones, such as Cadia. Okay, I'm not going to talk a great deal about this, but we've had a brief mention of these previously. If you have limestones or other carbonate material in the sort of contact aureola of these systems, you can get skarn deposits. So we have the calcareous rocks will transform, associated with the heat and the flow of the fluid, into minerals such as garnet, pyroxene, and wollastonite during metamorphism. And this is referred to as the prograde assemblage. As the system cools and fluid is reintroduced into that system, we get the retrograde products. And these include epidode replacing garnet, or chloride and actonolite replacing pyroxene and quartz. So we have complicated metamorphic history, and this is broadly showing how it operates. We have reactive skarns, a magma transfers heat and potentially fluids and other elements. This metasomatically alters the skarn. And then this is in the prograde stage, and then we might introduce external fluid somehow, and that leads to the retrograde metamorphism of the skarn minerals. So here's some just broad definitions. So isochemical is just metamorphism is generally considered isochemical. It's metasomatic is when we have a change in the chemical components. Exoskarn outside to the intrusion, endoskarn inside, so it's in the intrusion. Prograde, increasing temperature. Retrograde means decreasing temperature, and it's commonly a hydrous process because metamorphism has lost water during prograde progression. So we need to reintroduce water to back react the system. Here's an endoskarn. You're all pretty familiar with this one. So we're not going to dwell too much on this one. Here's an example of a retrograde effect. We have garnet, nice garnet here, surrounded by what looks like calcite. And we have pistachio green epidote replacing that garnet. Epidote is a hydrous calcium aluminosilicate. So we're competing with the groschula, so the calcium aluminous garnet, during a back reaction of the prograde sequence. So as we move deeper into the systems, away from the porphyry style, we have fluid pressures are lower, so we can't form massive brecciation or that style of the porphyry system, and instead we focus into structural controls like veining, where the vein actually breaks the rock through focused fluid pressures. We could get stockwork, so we have conjugate systems, or we could get closely spaced veins, sheeted veins, or simpler systems. And these are common for things like tin grisons, porphyry moly, polymetallic skarns, mesothermal veins. So here's our top of the granite. We can form this grison zone where we've concentrated the fluids. And then these systems have stagnated at deeper levels because of lower temperatures, as well as reduced conditions. They contribute to distinct metal deposits. These are common S-type systems. So tin and tungsten are concentrated more proficiently in these reduced systems, and we can form things like sheeted veins or simple veins systems. We might also get moly and the like in here, and we could produce pegmatites with unusual minerals like lithium. So these are associated with S-types or very unusual I-types, like in the New England area, which probably have a high sedimentary input. They crystallize at deeper levels. They are quite viscous. A lot of their fractional crystallization undergoes due to secondary boiling. So we have the late stage products after we've crystallized a large proportion of the granite, and that contributes to the preservation of tin and tungsten. They're not easily incorporated into earlier minerals. So then the fluid overpressure fractures the top part, the carapace, and the veins form in a parallel sheeted or stockwork style. So why are they distinct? So S-types are generated generally in the mid to lower crust, partial melting from significant metasedimentary material. They're generally colder, so they therefore can crystallize at deeper levels because they intersect their solidus much quicker. They are very hydrous. This contributes to their crystallization sequence and the concentration of tin and tungsten early. And they can undergo significant fractional crystallization, as associated to second boiling. So here's just an example of a Greisen deposit. We have this coarse-grained sericite, predominantly as muscovite. Coarse-grained muscovite quartz replaces the rock, and it's quite hard and resists weathering in this case, so we have Greisen halos. But we might also get things like tourmaline, fluorite topaz, and beryl, so these late-stage minerals rich in incompatible elements, but we can get all minerals including cassiterite, tin oxide, wolframite, so tungsten, bismuth, and moly. Here's an example from the Mole Plateau. We have the remnants here is the essentially quartz cassiterite, is the Greisen, and they've actually mined a lot of this regolith material which contained a lot of cassiterite or tin in systems a bit similar to this, where we have a cassiterite vein here. These dark minerals are cassiterite with smoky quartz, and then around it is this Greisen, so quartz and muscovite alteration features. Here's an example of a sheeted veins. This is this sort of system here. We see this prominent close vein spacing. Some people's deposit is classic for this. In the vein we have quartz and cassiterite, and we have a prominent Greisen alteration, muscovite and quartz. It's fairly fine grained in this case, and this host rock is predominantly a ignimbrite. And that's all for this week. Sorry, not for this week, for this lecture. There'll be another one soon.